of my talk is borrowed from a phrase that I think was coined by Zamolodchikov, and that's at least where I encountered it. But I also have a disclaimer that this talk is going to be from a condensed matter physics perspective, because that's what I am. There was a similar talk given in ICTS, a similar talk as in something to do with overlaps between condensed matter and high energy theory. And when I was back there, and the speaker began with a show of hands asking, how many people identify themselves as condensed matter? And Professor Loganayagam Ramalingam put up his hand and said, I'm a condensed matter theorist. Of course, the speaker was a bit annoyed, saying, look, it's not like I'm asking you how you identify yourself. It's more like, I want to know what your training is before I start talking. And he had this huge rant about how, in theory, all of high energy theory is condensed matter, and that's how we should all identify. So perhaps this disclaimer is not, maybe it's something that he picked up at TIFR, and this disclaimer is not necessary. In any case, for ordinary mortals, condensed matter physics is, asking questions like, what is the difference between liquids and gases and solids? Perhaps the first elementary introduction to condensed matter is that. You can ask why is ice, for example, very solidy, and why is water very liquidy, and why is steam very gassy? We could also ask questions like, why does one abruptly transform from one state of matter to the other? Right? So these are the questions that we can ask about. And a nice way to encapsulate all of this is the notion of a phase diagram. For example, we can have two parameters that we vary, pressure and temperature, and we know, water molecules organize themselves into solids, liquids, and gases. Right? So these boundaries are, when suddenly something that's very hard becomes something that's very soft, things of this kind. Right? Condensed matter is supposed to answer questions of this kind. So we do make some progress. Right? We understand that why is a solid different from a liquid? Why is a solid different from a gas, and so on? This is a very sophisticated theory, for something that's so prevalent in everyday life. Right? We can ask, what are the symmetries, for example, that's left behind when we look at the free energy minima that describes all of these states of matter? So liquids and gases, for example, if you take all the positions of the molecules and then shift it by any real number, the state that defines the system, for example, the Gibbs state in statistical mechanics, remains the same. The probability distribution does not change if you take all the gas molecules or liquid molecules and move them a little apart. And whereas here it's not the same. So you can only take all the positions of the liquid ice and then move them not by any real number, but you have to move them a certain discrete amount, and only then you come back to the same kind of a distribution. So the state does not remain invariant with the full set of symmetries as liquids or gases, but the same as solids. So wonderful phenomenon called spontaneous symmetry breaking describes many things, starting from superfluids, superconductors, solids, magnets. In fact, some version of that appears in high energy theory, but not exactly the same. Well, all that is well and good, but then what happens with gases and liquids? So you could ask, what kind of symmetries leaves the gaseous state and the liquid state alone, and you'll realize it's the same thing. Right? Before we discovered freezing water, we discovered how water boils. And the boiling of water is a very ubiquitous and a reliable phenomenon. Right? People have been making tea way before they started making ice cream. But then it seems like our theory does not distinguish between the two of them. Now, perhaps it is very possible that asking what symmetries are broken, as it were, is not really the right question to be asking. Maybe there's something else we could ask. But it turns out the answer is, in a sense, much more simple, which is, in fact, liquids and gases are not distinct phases of matter. At room temperature, if we increase pressure, or at standard atmospheric pressure, if we increase temperature or decrease temperature, we can move between these two states. But if we increase temperature to a sufficient degree, beyond what is known as a critical point, they become virtually indistinguishable. You can go from one to the other without encountering any free energy singularities. Right? So this is the state of affairs. It's actually, the symmetries are the same, and it seems like the theory once again gives us the same answer. But why does this thing exist? Why does this transition exist? Right? If you look at any material, like say carbon dioxide, nitrogen, helium, and you look at the phase diagram by varying pressure and temperature, you get more or less the same thing. There exists a range of temperatures and a range of pressures for which the liquid starts boiling and the gas can be condensed to a liquid. So this abruptly terminating critical surface, it's a finite segment. It's a phenomenon that exists across many different materials and in many different theories, in fact. And so one requires, the answer that the two of them are the same phase of matter actually begs the question as to why this critical surface. What is the critical surface supposed to separate? It's like a wall that separates two distinct phases of matter. But here we have the same phase of matter, and there's a wall that's separating nothing. It's like somebody decided to build a wall, but just stopped in the middle. You would be wondering why they did that, right? You might finish it or not start it to begin with. So in a grand scheme, I will not be talking about water specifically. In fact, I do have things to say about the liquid system, but I will abstract this question away and then just give the answer, or rather what I think is the answer to begin with. So what we could do is, in fact, think about these things as some coupling constants, say lambda 1, lambda 2. Like, water has some parameters, and then we can just keep adding coupling constants, say lambda 3, lambda 4, lambda 5, and so on and so forth. We can just take all the collection of states that belongs to the same phase of matter. So just keep tracking each state, and if you find a singularity, just avoid it and keep going, and so on and so forth. So this infinite dimensional space, in this infinite dimensional space, we can collect all the points that correspond to the same phase of matter, and we can ask what shape that belongs to. Right? My claim is that this has some non-trivial topology.
What do you mean by coupling? I mean, you had thermodynamic parameters which you replace by coupling.
Right.
Are you going to couplings of the microscopic field?
Yes, I do. So I'll treat them on equal footing. That's what I mean.
So this is a space of what?
Space of the entire theory. Like all the theories correspond to the same phase of matter. So for example, the solid would be somewhere here. They are disconnected. Right? So this is the liquid and gas fluids all together. So these critical surfaces are basically the presence of these incontractable loops, spheres, and so on and so forth. So if you look at the collection of states in some high dimensional sphere that wraps it, my claim is that these critical surfaces that abruptly terminate appear as obstruction to these contractions. And in that sense, they appear very naturally. Right? So this seems like a cute story, but how would one go about even beginning to ask why is this true if it is true at all? Right? So the question is naturally formulated if we move on to what would be a more theoretician's friendly way of looking at studying phase of matter. So recall that the most powerful tool we have in understanding long wavelength properties such as phases of matter is renormalization group. And so we have something like this, lambda 1 and lambda 2. Let's say two coupling constants. Typically, this is how it looks. So there are flows under renormalization group, like coarse graining. The theories would flow together in one direction and then away in a different direction. Right? So if you track the flow of any bare coupling constant, they have some trajectories of this form. There are two things that we really like. One is this critical surface, as it's called, where there are attractive directions and repulsive directions, and these other ends where they only have attractive directions and no repulsive directions. So roughly speaking, this surface with both attractive and repulsive direction correspond to critical surfaces where we have phase transitions, whereas these fixed points, as they're called, correspond to stable phases of matter. Right?
That surface you meant, right?
This is what?
That surface, not that surface.
This is a phase transition.
I was saying that was the critical surface. Yeah.
This is the critical surface.
Right. You're flowing towards that surface, and then there's a relevant operator on that end.
Right, so these are relevant. So the critical is when you tune away.
I see,
the
sorry. Yeah. I thought you meant the field theory surface. Sorry.
Right?
Yeah, got it.
So now we call them fixed points. But are they really points? Right? Maybe they are, yeah.
But you are not calling this one critical also?
This one?
Yeah.
No.
You are not calling that.
No. So this is your, let's say, typically, if you're very lucky, and we are often, this is described by conformal field theory.
The line of points where the low energy dynamics is conformal is what he calls it.
Yes.
The points in Faraday's space where if you go to low energies, you have conformal dynamics.
That's right.
Well,
That
all
is-
of those points.
What?
All of those points.
are like that.
Not points here.
Just along this.
On that curve.
Well, why not? I mean, take another point. You go to that fixed point, right?
Yeah, but that's not conformal. So typically, this is zero infinite correlation length fixed point,
Okay.
and this is a zero correlation length fixed point.
Massive.
But it could have been conformal.
It could have been, yeah.
Okay. In that case, you would call.
So it's typically
higher dimensional thing.
But critical surface associated with a particular fixed point. The critical surface for that fixed point is that line.
right. So if you're really lucky, this fixed point is described by conformal field theory, which we can understand fairly well, and this fixed point is described by some kind of a topological field theory, which is also sufficiently well behaved that we can understand them well. Now, the question I want to ask here is this really a fixed point? We call it a point. You know,
But,
is it?
but you could have conformal field theory without any relevant operators.
That's true.
Okay.
That's true. So this could be one of those two. That's true. Let me just make life easier and say that's not what I'm looking at. Just make it easier. I am not. This is just I just declared something. So I'm saying that these abruptly terminating first order transition that separates liquid and gas is, if you imagine it correctly, it's at the heart of some hypersurface, contractible, non-contractible hypersurface. Right?
In the phase diagram, water, liquid, and steam, each line is a CFT, is it?
It's not. It turns out here it's something called a first order transition. Only this fellow here is a CFT. But in my world, there's a lot of prejudice against first order transitions. I don't understand why. In fact, the most common explanation in condensed matter theory is character assassination. They would just say, these first order transitions, they have this tendency to abruptly terminate, which is true. But a few years ago, a bunch of us discovered that second order phase transitions described by conformal field theories can also terminate. Then, of course, character assassination doesn't work anymore, and we need a better theory. And this is my, guess at a better theory.
Sorry, I missed the beginning. What are you trying to? Could you say in
Right.
your goal?
Yeah. So the idea is, typically in phase diagrams, you have these frequently occurring, abruptly terminating critical surfaces. The question is, why are they so ubiquitous and so robust? In other words, they can be reached by, it's a codimension 1 surface or codimension 2 surface. You obtain by tuning only 2 of the infinite number of parameters. And my claim is that one could understand this, what the argument I'll try to make is that we can think of this as the theory space that corresponds to the entire phase, a single phase, has non-trivial topology, and these are obstructions with contractions.
So there can be multiple such surfaces
Yes.
in the theory's
Yes.
space?
Yes, and in fact, I'll argue that there are. Okay. So coming back to this point, is this a point? Maybe it is. Maybe it's not a point, but it's like something like a fuzzy sphere, but really has the same topology as a point. You can just contract it, or maybe not. Maybe it's something like this. Maybe it's something like this. Maybe it's much more complicated and much more interesting. It has all kinds of non-contractible loops, spheres, and so on.
What has all? Sorry, what?
The moduli space of fixed points. So maybe the fixed point is not really a point, but it's an entire surface with a non-trivial topology, and it has interesting physical consequences.
Are you saying that only for the massive point, only for the gap point, last point, or
I'm saying I'm claiming that this is true for
any critical
gap, at least for gap theories. This is almost always certainly going to be true.
So as you move on that space, what changes?
Yes, I'll try to make the argument. So this is the executive summary of what I'm going to be arguing. So why, does this have physical consequences?
So it's like what changes is the topological field theory.
Yes, there's a moduli space that corresponds to the fixed points. If you track a thing, it will be one of these points, but it's actually a non-trivial thing. There is a discrete data associated, right? Classifying them is discrete. Yeah. A single one has continuous automorphisms. Yeah, but I'll keep things much simpler. I won't use heavy TKFT machinery, but maybe private conversations I can say, but I'll keep it much simpler. So the way I'll do this is, condensed matter theory inspired. So I'll start off with microscopic models. And then I'll keep switching between this and effective field theory. And then I'll distill this into a set of beautiful mathematical framework. There's a mathematical framework that's slowly emerging as to how to understand all these things. And this we can once again use to, physics out of physics, the maths out of physics, extract physics out of this and then construct new macroscopic models, analyze that using field theory, and the whole thing is nicely consistent.
So of the two things you said, I didn't understand the connection. One question was, why do lines of first order phase transitions or whatever end?
Yeah.
And the second was, in this topological phase, could there be some structure?
Yes.
Why are they what
So the
relation
claim is
between
that if you look at what happens, what does it mean for this loop to be non-contractible? It has to exit the phase at some point. So there's a spectral gap that has to close. It's not a phase transition because it's within a single phase. So this obstruction to contractions, which is sometimes called diabolical points, is what we can interpret these things as. So there exists some kind of a sphere that you can wrap around and then.
So you're saying the first order phase transition. So can you say the connection again? What is the connection between these things? And
So there exists in theory space a sphere that you can wrap this around, which you cannot contract. So this has non-trivial, like say pi 2.
I see. So we're
For
away
example.
from these critical kind of things. So we're looking at massive phases.
Yes,
And these are those massive phases.
exactly.
I see. And the fact that the thing ends, what does that translate to here?
Oh, it's this just like, let's say you can have a line here. So the thing, the obstructive contraction, there's something that has to happen in between. Something has to give. So it could be like some nerve like this, which is a point, or it could be it has some width or something like that. That's the terminating part.
I see. I thought you were going to say that some cycle contracts at that point. That's not.
Cycle cannot contract at that point. It's the obstruction, so it has to exit. It has to go out of the gaseous phase. So this is that the surface where it exits the gaseous phase.
Is there something like cross section of that
Cross section of that.
of that torus or something like that?
So it's a squishy thing. Like it's not really a two-dimensional object, but there are many theories. It has the same homotopy type as a torus. Maybe if I continue the examples, it'll just make it better.
I should think of whatever this space you are drawing as that space, right? Or is that
This is the much simpler object, because if you look at the moduli space of fixed points, it's of smaller dimensions. Here there are infinite number of coupling constants I can add. I can literally change the coupling constant for each atom, and that's a different theory. So infinite number of coupling constants. That's how we always think about condensed matter. It becomes something that we can track by use of renormalization group. Ghost graining.
So are the states in the theory space given by points on this some two-dimensional surface? Is that what?
The fixed points I'm claiming, it's not two-dimensional. In my picture, it's two-dimensional. In fixed point, I'm claiming that it's some nice topological object. It's a nice topological space, which we can do homotopy theory on and then understand.
One question, if I am looking at a first order phase transition, is it in general clear that I always have a low energy theory for a first order phase transition? Because they are often just energies talking to each other, right?
Right.
Some energy going lower than something else. In that, is it clear that that energy difference is always due to some
No,
long
it's-
wavelength modes or something like that? Because other than that, none of this would work.
Two things. One is that it's everything apart from this. I'm claiming that the states around it is what I'm excising all the critical surfaces and so on, and just looking at the space of states surrounding it. And then, if I find that there's a non-contractible loop, something has to happen in between. One of the many things that can happen is first order
No,
terms.
that I understand, but by the time you are going to field theory and going to use argument,
Right.
you are basically saying that first order phase transition can be understood in terms of behavior of some long wavelength modes, which is true for a critical point. I have no
Around the surrounding states, of the surrounding
or in
states.
the surrounding state,
Right.
right?
Right.
Is that statement in general true? At least I don't know of an argument that it should be true for a first order.
If it's not, then I'll just restrict myself to cases where they are.
Okay.
A version of that statement I think is true,
No,
right? But I don't think I can do better than
wondering
that.
if there's some argument that this should be true. That's
Not that I'm aware of.
Just continuing with Rajit's question, couldn't there be a situation where these low energy theories are just trivially gapped? All of them.
This is the example. Like it can't get more trivially gapped than a gas.
So then I don't understand what this is.
Yeah. So let me So let me give a model that is trivially gapped. So this is called the Rice-Millet model. So it's a model of, it's a 1 plus 1 dimensional model. So it's a 1 dimensional lattice model in 1 spatial dimensions. And the Hilbert space is that of 1 fermionic mode per site. So there are two possibilities. One, yes fermion, no fermion. That's it. So the Hamiltonian I'm going to write down is very simple. So J labels the sites. There are two parameters. There's little delta and then capital J. So this is the model. So let me just describe what's happening here. There are fermions which can hop between sites. The hopping amplitude is staggered in the sense that here it's 1 minus delta. Let me label this 1, 2, 3, 4, 5, and so on. And here it's 1 plus delta. This is a 1/2. So the fermions can hop on either side with staggered amplitudes. And there's a chemical potential which is staggered too. So there's chemical potential of plus J here, sorry, minus J, plus J, minus J, plus J, and so on. So this is my model. Now there are two parameters, delta and then J, and then I'll vary delta from -1 to 1 to get a nice phase diagram, and then J from -infinity to infinity. So it's a phase diagram on a strip. So it turns out that this is the phase diagram, right? Literally, like this is a phase diagram consisting of a single trivial gapped state. There's nothing non-trivial about it whatsoever. In fact, they're all adiabatically connected. If you tune parameters, you'll realize that it just becomes fermions sitting on different sites or different bonds. That's pretty much it. So that's true everywhere except for one point, which is over here. So this is the origin, 0, 0. Okay, so let me unpack this. So this is a model that's quadratic in fermion creation and annihilation operators. So we can pass on to the single particle framework. So I can analyze this using band theory. So it turns out that, you see, I can naturally assign a 2-site unit cell, like this. Right? So it turns out that whenever you have a 2-site unit cell, you have a first quantized Hamiltonian with 2 bands. So you can assign a single particle description with 2 bands, and they have this dispersion. So let me just write that. So C dagger of K alpha, H alpha beta of K, C beta of K. So this, by passing on to the momentum space creation and annihilation operators, we can just write it in this way. So this is alpha equals 1, 2. So there are 2 flavors. So again, let me just look at the band structure here. So away from the origin, the band just looks like this.
Alpha is like either site 1 or site 2, that kind of stuff.
So when you go on to momentum basis, there's no site 1, site 2, but it's related to that. It's indeed related to that. Right. Right. So the band remains open everywhere in this phase diagram, except for the origin where the band closes. Okay. So this band closing is of a very particularly striking kind. It's a band crossing that happens linearly. Right? So the linear band crossing is evidence of the fact that, I mean, you can once again, you can consider the low energy theory for this point over here. So let me just move ahead and do this. Where's the eraser? Right. So near the origin, we have this linear band crossing, K epsilon. So in order to understand the low energy properties, we can consider the modes that live very close to this point. It turns out that this is for momentum K equals pi. And then we can pass on to an effective field theoretic framework. And the field theory here is very simple. It's a linearly crossing single band. So it's exactly a single massless Dirac fermion. So I'm going to be using Euclidean space, so where I think it's psi bar, delta. That's it. So psi is a 2-component fermion, and that comes from the fact that it's a two-band model, and this is precisely the low energy theory. Now we can go away from the origin. So very close to this point, very close to the origin, when J and delta are very small, right? We can ask what is the correction that appears to this field theory term. It turns out that the answer is the following. There's J, which is the mass term, and delta, which is psi bar gamma chiral. Right? So the two parameters appear as two mass terms for the 1 plus 1 dimensional Dirac, free Dirac Hamiltonian, free Dirac Lagrangian, and we can ask what else could there be? Right?
So this, what this is psi bar and gamma.
Psi bar psi?
This chiral.
Oh yeah, sorry. Gamma chiral is it's a two even dimensional space-time dimensional Dirac fermion. So there's a chiral mass, and that's precisely it.
Sorry, can you explain the two curves in this epsilon and k plane?
Right. So it's the first quanta is Hamiltonian, H alpha beta. It's a Hermitian model. It's a Hermitian Hamiltonian. It's a 2 by 2 Hermitian Hamiltonian, which tells you the energy levels of the single particle, like the two bands of the single particle, and these are precisely the energy levels.
And what do those crossing mean? As in, what's the significance of?
Right. So whenever the energy levels are separated, one above 0 and one below 0, right? It turns out that this is a gapped state, trivial gapped state, because you see there are a bunch of negative energies and there are a bunch of positive energies. The many-body Hilbert state, the many-body ground state, is just occupying by Pauli exclusion principle all of these states that are negative energy. So the total energy is the net energy of all the electrons. The electrons, all the electrons that have, fermions that have negative energy, if you add them up, you can lower the energy further. So once you add up all the energies, then you're done. So that's what is called a gapped insulator. Right? So this is the trivial gapped state that we have over here. The gap closing tells you that there's nothing you can do to make this a gap theory. In fact, there are low energy excitations that you can excite a fermion from here and then increase its momentum, and that's a gapless theory. This typically describes a metal, but in this case, it's called a different kind of metal. Well, that's the answer.
So, sorry, at the low energy theory, at the critical point was a
Right.
C equals half, comma half.
C equals 1.
C equals 1, comma 1.
What is comma? Oh, the scale.
Left and
Yes,
right.
it's half, comma half.
Half, comma half.
Yeah,
Half, comma half. Okay. So we've got one left moving fermion, one right moving fermion.
that's right.
And now if I want to make a mass, I combine the left and the right, right?
Yes. So this has all these left and right linear
And what is the
combinations.
second term?
The chiral gamma. So there's 1 plus 1 dimensions. So there is gamma 0 and gamma 1. And you multiply them together with factors of I, with a factor of I, then you have I, gamma 1, gamma 0.
And just in terms of the left and right moving fermion, in terms of the left and right moving fermion, this is psi left, psi left.
Oh,
That guy, psi bar psi was psi left, psi right, right?
psi left, psi right, that's correct.
And this guy is psi left plus
No,
minus psi
I
right.
think this will be psi left, psi right, psi left, but with opposite.
Correct,
sides.
that's right, that's right.
I see. I see, thank you.
Okay. Now we could ask what would happen to this phase diagram. So it's a two-dimensional phase diagram which is extremely boring. There's like one trivial gap state, except at the origin where the gap closes and you have a gapless theory, right? Maybe this is a stupid phase diagram because I just wrote a very fine-tuned model, right? I wrote a model with two parameters, and so maybe this is genuinely boring. And maybe this point you can just add a single parameter and then it just disappears. But this tells you that's not possible. Why? I can add any other term, but when it comes to the effective field theory, the only relevant parameters that you can add to the two-dimensional gapless Dirac theory are the two mass terms. I recall that for fermions in general, interactions are irrelevant. For 1 plus 1D, interactions are marginal. We'll come to that later. But certainly there are no relevant perturbations that we can add. So write down any term in addition to this. In the low energy theory, this would just renormalize this fellow and this fellow over here, and then all you get is a two-dimensional mass term. Okay? So this phase diagram, whatever it is, you can add any perturbations, and this gapless point will just move in that direction. So my claim is that this is a picture for what is a non-contractible loop in theory space. So the rest of the the next few minutes I'll explain why this is a non-contractible loop and how we can visualize this and all of that. But this is what it means to have an obstruction to a non-contractible loop. So indeed, this is not a terminating first order line, but it's a line, a defect that exists in theory space that you cannot remove with any kind of perturbations. You can add infinite number, it's always going to be a codimension 2 at least defect.
Sorry, in that delta and J plane, there is no such line, right?
The entire plane is a plane, so you can't have a line, you have a point. Add any other parameter, that point becomes a line.
Sorry, can you repeat?
So in a two-dimensional plane, a defect can be a point, is a point. You add any other parameter over here. Let's say, for example, next nearest neighbor coupling. Different kind of a chemical potential. You can add many, many microscopic parameters. In that space, this just extends as a line.
But already in the 2 dimensions, that point would probably have some.
Exactly.
Clearly,
Yes.
some non-trivial
Indeed.
topology.
Indeed. Right. So let's visualize this non-trivial topology very explicitly.
Sorry, I still haven't understood. So
Yeah.
it's psi left, psi right, I understand.
Yeah.
And now is it I times psi left, psi right? What is the other thing you will do, Sean?
So this is the.
Can you just write it in terms
so
of psi left and psi right?
I actually don't know this left and right thing. So then.
Psi left is just 1 plus gamma 2, right?
So maybe let me just do this. So this is psi left and psi right. Is that correct? Okay. So then in this case, this would be psi left, psi right. Let me just write down explicitly. This is 1, 0, 1, 1, 0, 0 minus 1, psi left, psi right. That's this term over here.
So your gamma 0 is sigma 3.
That's right.
Okay.
Right? I mean, this is a nice choice of basis. That's
Okay.
all. To give. So this one would be
So it's psi left, you say.
psi left. That's right.
So it's not Lorentz invariant.
This is, why is it not Lorentz invariant? It should be Lorentz invariant.
Because we have dz, d sigma plus, d sigma minus, and then psi. Should how does that work? So, it has spin, right? So if you have psi left, it has
That's right.
a total spin. It transforms under rotations.
So this is psi dagger, sorry, psi dagger. Right. Made a mistake.
So it's not a real form. So
It's not a real fermion, it's a complex fermion.
So then you're looking at a 1, 1 theory. C equals 1, C equals 1, 1. Your left moving fermion itself is complex. Is that right?
The total central charge is 1.
I sigma 2.
Total central charge, left moving central charge is 1, and right moving central charge is also 1.
No, it should be total central charge is 1.
Total central charge means
Left plus right, I think.
So why fermion?
a free boson has total central charge 1.
Yes.
Then it's two fermions.
Isn't it spinless fermion? Spinless fermion.
There's no spin in 1 plus 1.
Well,
No, but if it's the same kind,
it's the same thing that
as a free boson.
it is the same thing as a free
There's
boson.
2 left moving fermions.
I see.
And 2 right moving fermions. Then you can have two masses. Then
I see. Okay, good.
because it's like the left moving. Yeah.
Okay. Apologies, this is not a language that I am familiar with.
No, I'm
so
sorry.
this.
I'm sorry for
Yeah.
dragging it.
Oh, it's okay. Right.
A complex fermion is like a free boson, right? Yeah.
So psi bar is your I times psi dagger times gamma naught, right?
Sorry? Psi bar is psi dagger times gamma naught, yes. This is psi dagger, this is gamma naught.
I sigma 2, right?
Oh, right, okay.
Oh, I mean,
Yeah.
depends on your basis, but.
It should be square 2 minus 1.
Two sides together.
No. I use Euclidean signature, so it's always going to be. Yeah, yeah.
This is sigma 2.
Yeah, yeah. Well, it can be sigma 2, sigma 3, it depends on your choice of basis.
Yes.
Okay. So let me move on and then ask. So in the microscopic model, see, this is a Hamiltonian which I can write it. It's a 2 by 2 Hamiltonian, so I can expand it in the following way. So I can write it as vector G dot sigma. So it's a first quantized 2 by 2 Hamiltonian that gives you the 2 energy levels. So I can write it in this way. If I avoid the origin, there's a well-defined ground state which is the state with negative energy. Right? So let me define U minus of K.
So your critical point is exactly free boson and self-dual radius, right?
Yes, not at self-dual radius. Okay, depends on how you call it. Yeah.
But
Yeah.
free
It's
boson-
exactly a free
boson
boson.
Yeah,
Yes,
okay,
yes.
sorry. Yeah.
the lower band,
Abhishodh,
right.
this low energy, I mean, this connection that you are making with the phase diagram, the phase diagram was a purely the space of low energy theories, right? Because that was the phase, the low energy phase.
Near the origin is the low energy theory.
Near the origin.
Right. So when the parameters are very small,
No, but for large parameters also,
there is some low energy theory, yeah. But to describe that as a perturbation to a CFT is only near the origin.
so the phase diagram I should identify it with exactly this. I mean, even this temperature pressure phase diagram is like that.
But there will be statistical mechanics, but in that sense, yes.
And then you're saying the way it would be embedded in some bigger phase diagram,
Right.
you will have this feature continually.
That's right. Any perturbation that you can add, right, would just preserve this structure.
Yeah, but then I still don't quite. So if it is the non-controlled topology that you're looking at this point,
Right.
it's a topology. But when you have a wall that ends at some place,
Right.
that's not quite topology.
Right, we'll come to that. This will deform to that, in fact. Right. So the lower band we can assign. It's a collection of quantum mechanical states where you can rephase it. So there's a redundancy. Like, so this is the same as e raised to I phi of k, u minus of k. Right. So it's a k goes from k belongs to a circle. So u minus is the negative energy eigenstate. Of
You're
H.
looking at this a single particle Hamiltonian and your diagram.
That's right. So there's a very often used calculation, which is one can assign, like, so there's this redundancy. So what we have is over a circle is a line bundle. So we have a refacing freedom at every point over here. So we can define a connection over this.
What are you doing? You're looking at the space of single particle states around the critical point
No, this is around in the momentum direction.
in momentum direction,
Yeah.
but you're going to do it
At a
various
fixed point,
points
at various
around
points.
the
That's right.
critical point.
That's right.
Okay.
Right. So we can assign to this something called a Berry connection. Let me call this as AK.
So K is one dimensional.
K is one dimensional. That's right.
I'm sorry, that H was what again, please?
H was
what was G of K?
This is a single particle Hamiltonian.
Okay.
I just
Particle.
re-express this as, to expand this in terms of polymatrices.
And at the critical point, what was that?
At the critical point, it's the same thing.
Okay,
It's just a 2 by 2 matrix.
And
It's just form of these
this
coefficients
G
will
of K is
change.
something nice at the critical point?
Yes. It just gives you the linearly dispersing thing. So if I write this out, it's probably not very illuminating.
Okay.
But it is that.
Okay.
And here so G I should think of as in the delta J plane.
G would be a vector whose arguments would be in the delta, J, and K plane.
Okay. No, you're also keeping delta and J in the game, right?
Oh yeah, sure. Those are fixed.
Those are some
Yeah.
fixed numbers.
For
Because
now.
I was thinking that you might get an holonomy in the delta.
You would, but
Weird.
it's a different kind. It's not just on the delta J plane, right? So if I take this connection, we can define this transforms under gauge transformation. These gauge transformation exactly as a vector potential would. So we can define a gauge invariant object, which is I integrate over all the k direction, and this is what Berry has formulated. This is called Berry's phase, right? Now what I can do is just this is a phase. It's a well-defined number. It's a well-defined real number modulo integer shifts. Right? So it's a well-defined phase. Now I can just visualize this. I can take say for example gamma equals 0. I can just put an arrow in this way. Right? Gamma equals pi over 2. I can put an arrow in this way. Right? So for every point in the phase diagram away from the origin, at the origin this is not well defined because what is u minus is not well defined when things cross. Right? So just ignore that point and then just consider what the Berry phase looks like at each point in the phase diagram.
K space is a circle
K space is a circle.
because large enough K becomes same as 0K because you're
On a lattice indeed. So in condensed matter we call this the Brillouin zone. In the Brillouin zone in one dimension is the circle. Right? So if I plot that close to the origin, something very familiar emerges. So in fact you can do this for the entire phase diagram. It will be this structure which we should recognize as a vortex. So these phases wind around the origin in the exact same way as a superfluid vortex, and then you can go elsewhere, and then this does not change. So this is an angle, right? So A, you can just compute, like, so you can integrate that, and then you get an angle. So you can verify this. This is not some of the calculation that I've done, but it cannot be done analytically, in fact. But you can actually compute this and then just plot it on the phase diagram, and then this is what it
This
is.
is from the low energy.
It is not from low energy. So this I'll keep switching between low energy and high energy. Yeah. I mean, this is, I think, perhaps a prejudice that I have, like, which is one starts with microscopics and then field theory and then back and forth.
So from that effective action, you cannot see this?
Indeed, that's going to be my next step.
You can?
You can.
You can.
Yeah.
Wait, but the fact that it cannot change is because it has to be an integer, right?
It's not an integer. It's a U1 quantity.
Well, I see. So if you've come back to yourself, but that's fine.
Yeah. Right? So in fact, one could do something else, which is I can look at a connection not just over the momentum space, but over, like, let's take the origin, take any loop, let's say a circle, and then give this a new parameter, like theta. Right? So we can look at a connection over both momentum space and this parameter space. It's a two-dimensional manifold. So I'll call this A mu is del over del xi mu.
What was theta again, please?
Theta is you take the origin and then consider any loop around the origin and parameterize that as theta. Oh yeah, origin is the critical point, and then parameterize that by theta. And now there are two parameters. So it's a two-dimensional manifold. So the psi mu is the coordinate that parameters this two-dimensional manifold.
Gamma is changing and you still calling all of them the same phase? Or?
Yes. Yeah. I call it the same phase because you can go from one to the other without encountering a phase transition.
So xi mu can be delta j or k, anything.
Right. So I just take a loop. Right. It'll be xi mu would be theta and k. Like theta is like some parameterization. Let's say, for example, j square plus delta squared equals 1. Then j equals cos theta and delta equals sin theta. Right. This is any parameterization of a loop. Right. So what we can do is, if we have a connection over a two-dimensional manifold.
So in this case, this parameter space is a torus, T2.
Very good. Yes. So we can integrate this connection. Instead of integrating the connection over a loop, we can consider the curvature. Okay. Over, let me call it M2, which is S1, the Brillouin zone, the momentum space, times S1, the parameters, which is theta. So the two-dimensional manifold, right? With proper normalization, this is nothing but the first Chern number. And in fact, if you take this model, extract this, and make this computation, you get 1.
That's why it's the
Right.
same.
Indeed. So there are two things. One is we discovered that this phase diagrams, this phase in fact is called a featureless phase typically in condensed matter. But it's not featureless. It has a nice topological texture that emerges once you look at the Berry phase, a very commonly used the tool in theoretical condensed matter. In fact, it's measurable experimentally. One can measure something called electric polarization, and properly interpreted, it's a well-defined number from between 0 and 1. It is, it's not well-defined up to integer shifts, which corresponds to adding an electron or removing an electron. You can measure that, and if you make the measurement and then assign arrows appropriately, one should be able to actually detect this in the phase diagram. So this is the hint of a non-trivial topology. Okay. Now coming to Abhishodh's question, how do we understand this using the effective field theory? Right. So this is usually called a complex mass, and I can use a different way to write this whole thing, which is I can write this as m psi bar e raised to I alpha gamma psi. Okay. With alpha being appropriately tuned, so that m is square root of j square plus delta squared, and alpha is some arctan of this and this over that. Doesn't matter. It's some angle. Now, if we take this theory and then do renormalization group, how do things change? Right? There are two masses, independent masses, but they have the exact same scaling dimension, which is 1. Right? So if I do renormalization group on this, the overall mass term does renormalize. It grows. It's relevant. So this is m0 e raised to L. There will be a scaling dimension here which is exactly equal to 1. So this if you start off with small bare coupling, this would grow in this way. But alpha does not. It's a dimensionless parameter and it does not renormalize. Right? So at long distances, your fixed point is determined by m blowing up to infinity. True. But alpha is a U1 parameter that charts your moduli space of fixed points. And is exactly the same topology as the circle. Right? In fact, so we can just label the fate of our theory at long distances with the value of alpha that survives. And in fact, if you take the alpha, like I think, maybe I'm missing this, forgetting this, but this is, I think, pi minus arctan of delta over j. I think this is the answer. So if you actually just do the coordinate change appropriately, and if you plot this, you get the exact same texture as we did before.
Plot what against what?
So if you plot alpha, the term that does not renormalize, like eventually I'm claiming that when you let the mass flow at long distances, your effective theory, the vacuum that is described by just alpha, nothing else.
Yeah, that is just saying that as you are going around the circle, you are tracing an angle of 2 pi.
Exactly.
And you are drawing that as a vector.
That's right.
At every point.
Yeah.
But that vector was defined not as the phase of
Right.
j delta, but rather that thing there.
Indeed, that's right. Yeah.
So
what is the connection between this and that? I don't
not
know.
here.
I don't know. I actually don't know the answer to
No,
that.
but at this stage there is, you're just saying that as you go around, the angle changes by 2 pi. That's it, right?
That's right. So I'm saying that what we learn from that is that the fixed point is not really a point, but it's a circle. There is a
Depends how you approach it, yes.
Right.
From
So
which direction.
exactly.
That is clear, but I thought the kind of cool thing was that you can see that in this, single particle wave functions.
That's true.
That, which way are you coming?
That's true. Like the connection between the single particle wave function and the field theory, I don't have a direct answer. It's just that the two of them reproduce the same kind of a texture.
Couldn't you just define a very connection for this delta J plane in the effective theory?
In the what theory?
In the effective theory.
Indeed, you can. Like, so if you could consider the single particle for this continuum theory and then track it, you should probably get the same answer.
And you'll probably get a holonomy.
That's right. In fact, that might just connect to this directly. So that's the answer. So you just take the single particle Hamiltonian for your field theory and then do the same calculation, you get the same answer. But here you have an answer for it.
And that last calculation is at some particular k.
It's not at a particular k. So each, let me think about this.
I mean, it's about dependency.
At a particular k, right? At some k. And then
Right.
will the answer depend on what k?
So why some k? I mean, the
So
quantity
here
interest
it's-
is gamma, right?
It's gamma, yeah, it's
The
an
question is
integral
how,
over.
as you go around the Brillouin zone, what you come back to?
It's not the Brillouin zone. So you integrate over the Brillouin zone to get an angle,
Huh.
and then you take that angle and then look at it. So it's not around the
Exactly,
Brillouin
but
zone.
I first want to consider that angle
Yeah.
That's right.
at a given point in the parameter space.
That's right. Then you integrate over k. It's not a
Yeah,
single
exactly.
k.
So it's a question of.
Oh,
as
right,
you
right,
go
right,
around
yes.
the
Yes,
Brillouin
yes,
zone,
yes.
What do you come back to?
That's
That
right.
is your angle at that
Indeed,
parameter,
indeed.
And that should change as you go around.
Correct. Correct.
Right? So that first calculation,
Right.
I mean, why a fixed k? I don't know. I mean,
It's
somehow
not a
going
fixed
back.
k.
Woodruff's proposal was you compute the same thing in theory space without involving k at some fixed k.
Just pick some k and then look at the single particle United States and just look at the holonomy in the theory space. So you define a Berry connection in that. You can define a Berry connection.
You
in
can.
the theory space, right?
That's not what I am doing, but you
Without
can.
even involving k, any particular k.
So what you have is a mu, which is defined over k and parameters. What I was doing is integrate over k and then look at it over parameters. What Onkar is proposing is integrate over the parameters and then look at how it changes around k. You get the same answer. You should get the same
What's
answer.
nice here is that you, for a fixed theory,
Yes.
in the sense of fixing the parameters,
Yes.
you compute this quantity, that is a function of theory.
Yeah.
And then you see how that quantity changes as you move in the theory space.
Yeah, that's right.
Yeah.
But I mean, the problem is that in the effective theory, this thing is not compact anymore, right?
Correct.
The Brillouin zone opens up, right?
That's true.
It becomes a line.
That's true.
So
Indeed.
it's not clear to me.
Uh-huh.
I mean, maybe it makes sense, but
No, the circle is not well defined, so it doesn't make sense. That would be appear as a cutoff or something like that,
Yeah,
and
something
it would
like
depend on the cutoff, so it's not clear.
So you got this flux equals 1 here, right?
Correct.
This flux. That you were mapping to this winding being what? Being
Yes,
pi?
yes.
That is your mapping?
Correct. It's the same thing. You integrate 0 to 2 pi and divide by 2 pi, you get 1.
But as Abhijit keeps emphasizing, what's funny is that this flux was in a space that knew about k.
The flux is in the space that knew about k. Right.
It's in a two-dimensional space that knows about k.
Correct.
Whereas
Here it does not.
It does not.
Yeah.
So is it clear that those are the same thing? I mean, even conceptually.
No, it's not clear. But they give the same answer, is all I say. It's an observational statement rather than a statement
it's a
of
very trivial
fact.
same answer. It's
Sorry?
not like zeta of 3 or something. It's 1.
It's 1, yeah.
You get
No,
1.
it's an integer. It's an integer. That's the non-trivial fact is it's an integer.
Sorry, Abhishodh, I don't even understand this calculation. What is this calculation? This I should think of as delta, and this I think it should be j, right?
This is j and this is delta.
Yeah. So then this angle is bound to make this kind of thing.
That's always true.
Yeah.
But the fact that this describes a collection of fixed points is not obvious. And that only happens because the origin is described by a gapless Dirac fermion. That is a non-trivial statement.
Were you saying that the mass, this complex mass winds by 2 pi as you go around it?
Correct. Correct.
Yeah. And that you're saying, Abhijit, is rather trivial.
Yeah, I would think,
True.
right? Yeah.
So you have to find a formula for the phase of the mass.
Right.
And
But it is something
it
like
is just
that.
angle in this space.
Yeah, it's angle in that space.
So I agree. Yeah.
So the statement, the fact that the complex mass can be given a polar and radial coordinates is not, of course, a big deal, right? We learned that in high school. But the fact that this tells us, it guarantees for us that in your theory space is always going to be a codimension 2 gap closing point. No matter where you are 2 parameters away from closing the spectral gap. That to me is something too new to learn.
So then if you went to the IR, I mean in this case
Right.
maybe it's, I don't know how to think about it, but if you went to the IR you would get like a 1 parameter family of
Correct.
degenerate states or something like
There are-
TQFT or something like that.
It's not degenerate, but yes, it's a 1 parameter family
Of TQFT.
of
Of
TQFTs.
empty states. Or empty theories.
Of empty theories. It's still going to be a,
One parameter. It's just that your relevant deformation
Right.
has a phase, right?
that's right.
You're not really looking at the TQFT.
That's
You're looking at the deformation of it.
Well,
Or the operator on it or whatever. This mass, right?
mass
Is
indeed,
not part
but
of the TQFT. Or it is.
where it
is.
flows
Okay,
to.
It is.
Yeah.
I agree.
No, but that quantity is nice, right? I mean, if you can compute that quantity.
Yeah, that quantity is.
That's gamma is associated to a theory, and that's a quantity that literally is labeling their theory.
True,
right?
but I claim, I mean, at least there's a very good reason to believe that it's just giving us alpha. It's just a very complicated way of getting the same thing.
But I don't understand why that is the case. I mean, one zeroth order issue is that you don't have a circle anymore there. Like, how do you define this? gamma?
True.
There is no conclusion.
So there is an answer I can give, maybe, but I can delay it. There exists, like I said that this is a measurable quantity, right? There exists an operator expectation value I can compute that this is sensitive to, and that can be related to using this field theory. In fact, when I talk about bosonization, this becomes slightly clearer.
So suppose we forget about this calculation for a moment, just that.
Right.
Here you're saying in some space there's some winding phase.
Right.
And the only way that can be consistent
Right.
is at a point where the mass goes to 0.
That's right.
Is that?
No, absolutely that.
Okay.
Yeah.
So Abhishodh, are gamma and alpha the same?
Are gamma and alpha?
If you calculate this gamma, which
Right.
is the very phase, is it going to be equal to alpha or?
I don't know. This is just an observation that there are two ways to get this. They give you the same
this
answer.
Gamma can be, of course, easily calculated
Right.
because you know all the right functions.
That's right.
So do you get the same as alpha? Or
Yes, yes, you do. Close to, no, sorry. Let me rephrase my statement. Close to the origin, you get the same thing.
Yeah.
Away from the origin, the gamma actually has a very non-trivial way of moving about in the phase diagram, which is not captured by this, but only close to the phase, the part where it's described by a field theory, they agree.
So then you have e to the power of I alpha gamma is e to the power of I gamma square.
Sorry, gamma. Oh, that's the confusion. This is gamma chiral, the matrix. Sorry, my mistake. Yeah. So this is the chiral, it's a polymatrix. Right. Sorry, thank you very much.
By the way, don't you have two crossings in the Bruno?
Don't you have two crossings in the Bruin zone?
Yeah.
Away from the origin, you do not. There are no crossings.
I thought like at k equals to pi and k equals to 0, there are two crossings.
Not for our.
So that you have the upper. Like one crossing,
No, that's you're thinking of a different model. In this one, that doesn't exist.
Sure, both there.
Oh.
So just like pi and minus pi.
Right.
Yeah.
So you're having just
Pi
one
and minus.
minus.
Oh, yeah, exactly.
Yeah, okay.
Okay, I don't know how long I'm supposed to talk.
So we usually go on till about 1:15 or so.
Oh, okay, fine. Okay.
So, by the way, Abhishodh, this gamma I should think of as I'm moving along, let's say the bottom band,
Right.
How I come back to myself,
Correct.
right? So I could also define that for the top band,
You could also define for the top band.
and these numbers are related.
Yes, they add up to 0.
Okay.
There's a reason, but they add up to 0.
Sorry, is C1 and this Chern number and gamma related?
Correct. Because
I can't see from the plot.
so if you just if you integrate gamma over the circle, you get C1 up to 2 pi. This is 1 over 2 pi you have to do.
That is GA, this is DK.
True. They are, but not in an obvious way, I suppose. Yeah, Stokes theorem. That's the correct way. Yeah. Okay, let me move ahead. Right. So this would get more interesting as we go to higher dimensions. Indeed,
This quantity you can only define for a free theory, right?
this quantity you can only define for free theories.
Because
Yes.
you want a single particle state.
That's
so
true.
things are very special kind of quantity.
Very special kind of.
Whereas a theory space quantity is less special.
That's right. So this tells you about theory space. That tells you about free theories.
So it would be nice if there was a clear connection.
There would be. I don't
because
have
then
one.
you can go away from free theories.
That's true.
But I mean, more about, the philosophy here, as I'm seeing, is that you just look at the infrared phase.
Correct.
And if it is described by some massive theory, you can do this calculation massive theory, and then you're saying because it's kind of topological,
Right.
even if you add other parameters,
Correct.
which would make theory interacting,
Right.
would be, I guess, irrelevant parameters,
Right.
right? So that feature would survive.
That feature would
in this
survive.
transpose direction.
Yeah. So in fact, let's add interactions.
So just say again what you said, sorry.
I think he's gonna do. I mean, adding interactions to that, this robust feature will survive.
On the right-hand side picture or left-hand side picture?
So
Right hand side.
Right-hand side picture, yeah.
I mean, this by definition is non-interacting.
No, I mean here in this Lagrangian, if you add some stuff, as you said,
Right.
the diagram that you're gonna get is that there is extra dimension that you will add.
Right.
But this point will have its line
Correct.
going into that direction, right?
Up to a point, yes.
So this topological structure also is present even when you have additional
Indeed.
terms.
Which is why I say it's statement of theory space rather than just this particular model.
And in that context, if you don't want to do it in the free theory,
Yes.
could you just imagine defining Berry connection for the ground state?
No.
It doesn't work.
So it's a very good question. Can you define a Berry connection for a ground state defined on an infinite dimensional Hilbert space?
Yeah. For
No.
instance. In a gap phase.
You
right?
can't.
You
So
can't define
you
it.
can't. So it turns out that this is a subject of much recent interest. For quantum mechanical system, for finite dimensional Hilbert space, the Berry connection and all of this is very well defined. For infinite dimensional Hilbert space, you cannot define it. So there are two ways to go about doing things. One is you can use C-star algebras, and then that's what Kapustin and company do. So you can define something called a higher Berry phase using very complicated things like C-star algebras. For one dimensions, you can use matrix, something called matrix product states,
Okay.
right? Where you can extract not bundles, but the right mathematical structure is gerbs. So it turns out that for wave functions, many body wave functions, is a very complicated affair to assign the generalizations of Berry phase. But if you have a free theory, then they all reduce to like band structures, which is like quantum mechanical systems, finite dimensional Hilbert spaces, and you can use this technology. That's the reason why free theories are nice, of course, amongst many.
Past was special because it was a relevant operator.
Correct.
Is that right? So what your general structure will be, there will be a fixed point, there will be a space of relevant operators.
Correct.
And you'll look at the motion around that.
Right. So the two things, maybe I'll get to it, maybe I won't. So this story can be done independently for every dimensions, right? Now I can do 2 dimensions, 3 dimensions, so on, and then do the same thing. It turns out that they're all related. So there's a rather beautiful mathematical structure that connects the non-trivial topology of one spatial dimensions with non-trivial topology of all other spatial dimensions. So it's a very beautiful cascading structure that appears. And that I want to both describe what the framework is and then give evidence for its existence. So that's what I'll give.
So the right-hand side didn't seem to care about dimension at all.
It-
Just seemed to care about the space of relevant operators.
Correct. But I'm saying that as you go in different dimensions, the number of, in quote, independent relevant operators are not unrelated. It turns out that they have a relationship with each other.
I mean, it depends on which theory you're looking at.
True.
You can look at a theory with, let's say that the framework is you have a theory, you have a set of relevant operators, I tell you something about it,
Right.
and then you can try to do this kind of thing.
Correct.
And the final output will be that the topology tells you that there must exist a fixed point. Is that?
The topology tells you that there must exist some loci of gap closing points in between. Right now it's a point,
Okay.
but it can be other things. Which let me just give you what other things can happen. In fact, we'll meet our old water phase diagram again. Okay.
So in the mass case, it was totally trivial, right? Because mass has a phase.
Right.
So the only way that it can wind is if mass goes to 0.
That's right.
But we knew that the mass could go to 0. So
That's true.
It was not telling us much.
Right. So and maybe the deceptive part is the fact that I took a very tractable theory. I mean, one could play the entire game with interacting theories and then it becomes richer. But I claim that the essential features can be understood using free theories.
Will you give us one non-trivial example?
Yeah. So let me do that right now.
So just before that, just to get the language on the same page, very connection or very this thing, people talk about when there is some dependence on the parameter space.
Correct.
I want to distinguish that from this A so having subscript K.
Right.
So here that I understand as a thing that you define at a fixed parameter.
Correct.
And as you go around the Brillouin zone.
Correct.
Right. So I don't know whether you would want to call it a Berry phase, because the Berry phase usually fix the wave function as you said.
I mean, what is a parameter? K, if you interpret K as a parameter just as like J and delta and all that.
I mean, usually you wouldn't, right? I mean, you would,
True.
you just have a parameter of the
Berry
the
didn't.
theory.
To be more precise, Berry didn't, but we could.
Okay.
So we have a Hamiltonian that's parameterized. It's a 2 by 2 Hamiltonian. It's a quantum mechanical system, parameterized over a circle and a parameter space.
Okay.
So you can take a loop in anything. You can do a loop diagonally from momentum to all of that. There's always going to be a Berry phase that's well defined.
Okay, so if I not define this, if I just stick to Berry phase, because maybe a general proposal will involve just fixing a particular state like a ground state and see how that changes as you move around the parameter space.
Correct.
Right? And then is it clear that this particular observation here of the gamma,
Right.
so you define not quite a state. You didn't work with a particular state, but rather all these states, the eigenstates of K.
Right.
And then you define this gamma, and then you said gamma goes around like that.
Correct.
Right. But now if I instead fix K, and then go around the momentum space, the parameter space of that circle, then would I?
You would get the
this?
winding again.
And this is related. This observation is related.
By this.
I see.
So I think it's the same thing as
So I
Stokes
could have
theorem.
just stuck to one particular K and just.
You could have done that too.
Very connection.
It's what you just said a few minutes ago, which is you take the fact that this has non-trivial flux over or T2. You can just take a circle anywhere and then do Stokes theorem and you get the same answer.
Yeah.
But even that in some sense is not too sad, as you all are saying, that's fixing a K is associated with free theory. So it would have, the nicest thing would have been if you could just fix the ground state in the gap space and then look at its salon, right? That would
The
have-
many-bodied ground state.
Yeah.
That's true. You
It
can
would
do
be,
that.
like, so nice.
You can do that. In fact, you can do that. There's this whole Job business, but
Okay, you're-
maybe I won't get to that. I won't get to that. It's too complicated. Okay. So one final statement about bosonization.
So going one last. On the right hand side of the board, you didn't even talk about states. Right? It was just motion in parameter space.
In parameter space, yes.
There was no mention of what happened to any state in the.
Well, I did because under RG this flows to some trivial theory, gap theory, and that trivial theory I can track by alpha.
Okay, but I
So
don't.
that's a
I'm just
state.
saying it's just in the space of relevant deformations you had it. That's all.
In the space of indeed, but that it flows to a state. Like some like you have a unique ground state. Basically that's the theory. Like it's a theory, one-dimensional theory.
Okay,
It's a unique ground
maybe
state.
you can associate, but you don't need to. Right? You can just think in the space of parameters.
But I think the point is that here it's quite easy to visualize, right? Like you know that these are the parameters. But suppose you were trying to deduce the topology by
Without knowing
computing
the relevant operators.
or something, without knowing the topology of the space of relevant operators.
Without knowing that.
Yeah. Then how would you compute something in your field theory that would tell you that the space has non-trivial topology, right? That's the spirit of this.
Indeed.
Thing, right?
In fact, I'll give you the framework that gives you the answer. I thought this is more illuminating to give an example and give to the framework, but I might be wrong. Okay, interactions. So the original Rice-Milling model, I can add to it an interaction electron repulsion. So let me define it this way. So it's n is the number operator C dagger C, and this describes for you repulsion, some kind of a short range repulsion between the electrons. It's an interacting term. The halves are to fix the chemical potential so that you don't move out of the
Repulsion between J and J plus 1 is
J plus 1, correct. It does not erase well.
Sorry, what was A?
What is A? No, sorry, this is from the previous calculation. Right? So with interactions, the right framework to consider is if we bosonize the theory. Right? So once we bosonize the theory, it appears in the following way. So let me use the notation that we use in condensed matter.
So this was like a subtheory kind of.
Indeed.
Yeah.
Right. So where is U? It turns out that K equal to 1 for U equals 0. As we introduce, if we tune up K, if we tune up the interaction strength, K changes. In fact, we can determine the functional dependence of K on U explicitly using Bethe ansatz. The model that we have is Bethe ansatz solvable, so you can actually extract. The K is called the Latinger parameter. Typically in high energy, I think you absorb K into phi to change the compactification radius. But in condensed matter, we like to keep a compact boson radius 1. And then extract the thing that tunes the scaling dimensions into a coupling constant. This is called the Latinger parameter. So this has a particular form. This arc cos. Right? So it turns out that interactions introduce a particular operator. So there's some U cos 2 phi. So the operator scaling dimension for this cos phi is K. Is the same thing as cos phi, sin phi, e to the I phi. All of these trigonometric functions have the same operator scaling dimensions.
What was M?
M is the same thing that I had over here.
Okay, so in the critical theory, there's no M.
Critical theory, there's no M.
Okay, but even in the critical theory, so
This can exist.
yeah, so you can turn on these interactions and have a critical theory.
Correct.
All that does is renormalize the radius of the fiber.
Absolutely.
Okay, just the side of the ball.
Indeed. Yeah. Right. So there's operating scalar dimension. The mass terms have scaling dimension K. So for the non-interacting theory, you get back the scaling dimension being 1 as we expected. But interactions also introduce the higher harmonic for the compact boson. So this turns out to have an operator scaling dimension of 4K. Now you increase U to positive value, you realize that there is a range of interaction strength for which the only relevant deformation continues to be the mass term. After a critical value, this also becomes relevant. Right? So there's a 2-parameter family of mass terms that you can look at. So the fate of this coupling, this is called a dual frequency sine Gordon model. Like it's not very obvious how to do track the fate of the renormalization group flow of this. What we can do is just say that when both of these are relevant, we can just do mean field theory. Just take this as an effective potential and then minimize it to see where the vacua lie. Okay. Now, first of all, notice that since phi it takes values on a circle, the trigonometric function with the leading harmonic has a unique vacuum.
Sorry, so if we're in the range where this U cos phi is
Right.
irrelevant,
Correct.
then at m equals 0, the theory flows to a critical.
M equal to 0, theory flows to critical value.
Whereas if we're in the range where that U cos phi is relevant,
Correct.
then the theory never flows to a critical. Even when m is 0, it does not flow to critical.
Exactly. Right. Okay. So let me describe what happens to the critical point. So what happens? Like suddenly it looks like this. What happens to this non-trivial topology around it? So this U is less than 1/2. It turns out that this interaction is irrelevant. And you still have the same thing and the same winding. But the winding now has a different interpretation. Because you see, when the mass term is relevant, the long distance properties are completely determined by this. Right? It's just this operator has to be minimized. And this is minimized when the argument is 1. So there's very little fluctuation in the field phi. It just fluctuates a little bit about a particular value of alpha. Now, once again, we can track what the vacuum looks like, what is the value that the field is pinned to, and then once again you get the same winding that we had before.
Just because it's winding in the parameter.
Indeed.
Forget about what it multiplies, right?
Sorry?
M as a complex number
Correct.
winds.
Correct.
I
M-
don't even care what it multiplies, right?
M as a complex number winds, yes, indeed.
Fine.
No, no, sir. Here it sets phi mod phi is equal to this vacuum expression phi is equal to alpha, right?
Yeah.
So the vacuum is phi word, not trivially around that parameter space.
Vacuum. Alpha
Alpha was that phase in the parameter.
But and it's also that M does not appear with the phase there.
Now M is the,
Oh, I see.
okay, sorry, maybe I misunderstood you.
But you can probably write this as M e to the power I alpha times e to the power I phi plus M star e to the power minus I alpha times e to the power.
Correct.
So in that sense, it's just the phase of M. Right?
True.
But it's a property of the theory, right?
Exactly,
Vacuum expression
exactly.
value of phi
Exactly.
has alpha.
No doubt, no doubt. It's just you're changing the phase of the parameter, you're changing the phase of something.
Well,
I mean, I'm not saying the theory is insensitive to its parameter, right? But all you have to do is track the parameter.
Yeah.
so what happens when interactions are relevant? Right? We can understand what happens by just taking this theory and then looking at the vacuum, like what is the minimum configuration, field configuration. It turns out that for j equal to 0, right? For j equal to 0, it turns out that there's a new symmetry that emerges. It's an accidental symmetry along this line.
J was what?
So j was the x-axis,
In this. Yeah.
right? So there's a new symmetry that emerges, and that symmetry is spontaneously broken by that field, the interactions. So what you end up getting is you get a line. This symmetry that's spontaneously broken is explicitly broken away on the x-axis. So everywhere away from the x equal to 0 line, you still continue to get a unique vacuum. It just shifted. It's a minimum of some complicated potential that has wiggles coming from two different frequencies. But only at j equal to 0, it turns out that you have explicitly two spontaneously symmetry broken ground states. Right? So
What is the other axis?
so this one is the hopping delta.
Delta.
Yeah.
Yes.
So just to remind you, delta was the anisotropy in the hopping for the fermions, and J was the staggering of the chemical potential.
Okay. And U is some transverse direction.
U is some transfer direction. I've just kept U fixed for all of them.
And this is the case where there's no critical behavior.
There is no critical behavior indeed.
Okay.
So this is a gap theory with two vacua, and this exists only in one direction, and this terminates by the Ising critical theory. So the reason how the Ising critical theory appears in this model is a subtle affair. One can determine this is something called double frequency sine Gordon model, and we can track the critical flow of that, and then you can argue that through a process called refermionization, you can argue that that corresponds to the critical theory, the same universality class as the Ising model. So this is C equal to 1/2 Ising universality class. And around this, you have the same vortex behavior. Okay, this is the same kind of a first order transition ending in the Ising universality class as the water phase diagram. In fact, this is a commonly recurring trope. It appears in this model, it appears, for example, in the Ising model with the magnetic field, it appears in the water phase diagram. It's pretty ubiquitous. If you believe this theory has something to teach us about the other models, this is what I claim typically happens when you have a terminating first order transition. In this case, also happens to be ending with the Ising universality class.
So with the U, I should think of this as a cut vanishing and becoming a point.
Correct, correct.
Change U.
Indeed, yes.
There's a branch, this cut just merges.
Right. So other things can happen. For example, if I introduce chemical potential, right, I can change the chemical potential. This point, in fact, blows up to get a gapless theory. It's a metal. Like a partially filled Fermi surface, and that also disappears. The only thing that cannot happen is this vanishes. That's the only claim. There are three things that can happen. One, it can be a point. Second, it can be a line. And third, it can be a surface of a different phase. So it has to exit the phase and enter something else. It can either happen through finite codimension set of diabolical points, or it can be an entirely new phase that appears.
So, but this is a bit confusing because in the water case, you
Right.
said that when you talked about this solid and liquid,
Correct.
you talked about some sort of spontaneous symmetry breaking.
Correct.
And then you posed the question that there is no order parameter in that case.
That's right.
In the other case, so
That's
how is
right.
that? But here, you're getting more than what you bargained for, right? Because here along the dotted line on this side and that side, there is spontaneous.
No, there isn't.
I mean, there is this, this is Z2, on one side you have this side and so
Not on this side.
the vector
Along
changing sign, right?
on
What is
only along this line.
Huh.
In this model, there's an emergent symmetry, but it's some infrared thing.
Okay.
It's not necessary. So you see, there is just one phase. You can go from anything to anything without encountering a phase transition.
No, sorry. What is the significance of this expectation value of phi? So this begin with that as Z2 symmetry.
Right.
And
So
then-
there's no Z2 symmetry there. So let me explain in what sense this is Z2 symmetry. Now I can take this, right? Let me call this as V of phi. V of phi with fixed parameters, J and delta. Right? I can just play around with this potential. So it turns out that when J is not equal to 0, you get something like this. There's one lower and one higher. When J precisely equals to 0, you get something like this. So it's some infrared thing, like it's an emergent symmetry that appears only when you look at this potential, and so you can add anything to it. All that changes is this critical line tilts, becomes a wiggle, S-shaped, and so on. It's an emergent thing. You cannot remove it,
I see.
and this is what happens. Okay. So before I move on to the
This is really interesting. So you're saying that here the parameter wound, and you might have naively thought there would be one fixed point, but it's broken up into two.
correct.
And is there significance to the fact that the sum of the central charges of those two
I don't know. I don't think so.
is the same as the central charge?
A good point. I don't know. I don't see how, but I don't know.
From continuity in U, right? At some point, this continuity
Splits into that, and so it had to split up into two equal things.
Wait, I don't know. Is there some kind of a conservation law like that? I don't see why. There's a C theorem which tells you there's an upper bound. Well, that too has to be taken with a pinch of salt because we have to try under renormalization group flow C cannot increase. But apart from that, I don't see any constraints.
But sorry, how did you see, what did the Berry connection tell you about?
You can't.
Told you that-
So the Berry connection story no longer holds at this point because it's interacting. I don't even know how to do a calculation.
But you still have a phase and parameter space.
Correct.
M parameter goes around by 2 pi.
That's right.
And so m equals 0 has to do something funny.
Sure.
Right? Because it's going around 2 pi and.
Right.
So something funny has to happen.
Yes.
I think what's interesting is that it's not what you might have thought originally, that you get a single fixed point. Yeah.
But shortly the connection knows about it, right? Like maybe if one were able to do some version of Berry connection.
There is some version of Berry's calculation which is the Gerb story which you're saying.
Okay,
But I really don't want to talk about that. It's big red herring. Yeah.
No, but it's standard Berry thing, right? You look at a particular ground state.
Correct.
And then you go around like this.
Correct.
And see what you come back.
So there's a reason why that does not work for infinite dimensional Hilbert spaces. And the problem is this notion of thermodynamic limit. Right? So I have, let's say, 1500 spins and I get a Berry phase. But I add 1500th one spin, it completely changes. Because you see it's accumulating the Berry phase for all of these things. So if you track some U1 quantity in the thermodynamic limit, it's very ill defined. So you need to be able to assign these phases in a very consistent way, and you can't do it using the usual way you do this.
I thought the spirit was to compute something in the low energy effective theory that will tell you about this topology, right? So I sort of missed the point of what you calculated that told you that there was this splitting of the fixed points.
Oh, I just know how to do the calculation at the origin.
Of course,
Yeah.
you know, but
So
is there
the
some
topology, first of all, you can keep track using this.
Okay.
Right, very far away, you can keep track of what alpha is because this is an effective theory for the interacting model. So away from the origin, you can do that. Close to the origin, you have to do a different calculation. You have to minimize this potential and then see what happens, and then you can see how it terminates.
But in this
and
case,
then
there is no very phase-like quality.
microscopic.
Yeah,
No.
Okay.
No. As far as I know, no. I mean, I'm sure there's one. I just don't know what it is. Okay. So one last. Sorry.
Is there any discontinuity in this angle as you cross this dotted line?
The angle is not defined on the dotted line.
No. Slightly to the left, slightly to the right. Does it
Ah. Oh, good question. I don't know. I don't know. Maybe.
Sorry, I'm trying to understand where the sequence half theory came from.
Yeah.
So, can we see that by just
Yes.
from the potential?
Yes.
If we look at the
Yes.
potential and we tune things, you
Absolutely.
get a massless mode at that
Yes,
point.
yes. So let me tell you what happens along this line. So here, the potential looks like this. Okay. Sorry, it looks like this. It's a periodic function. V of phi 0 to 2 pi. Right. As you go closer and closer and closer, these two merge, and then you get a
Like
unique
a 5 to
potential.
the 4.
Sorry, I made a mistake. Yeah, indeed, it's like a 5 to the 4. So there's a periodic potential, this 0 and 2 pi. It has to, these two have to be identified. As you go closer to one of the ends or the other end, they either merge here or they go around and merge here.
And we know 5 to the 4 is like Wilson Fisher.
Exactly.
And
The
therefore
Wilson Fisher fixed point. So this is 1 plus 1d, it's Ising universality class. Okay, one final thing before I give the big picture. There are actually edge modes that appear in this slide.
One last bit. This thing can one, now this is of course a very crude picture because we're doing classical analysis.
Right.
Can one argue this seriously using conformity theory?
Which part?
That you get the sequence half modes?
Yes. So this is Delfino and Musardo.
And can you just say one word about the nature of that analysis? How is it done?
So what one does is, well, I tell you how they do it, maybe. So what they do is they do something called reformionization. They represent the C equal to 1 theory as two Majorana fermions with C equal to 1/2. And then if you track the parameters, you realize that you end up getting mass for one of them and not the other.
Okay, that sounds
So you-
thank you.
Edge modes. So let's, it turns out that all of these phase diagrams have edge modes that you cannot remove. So there is this gapless point here. You can study the theory with periodic boundary conditions and you can study the theory with open boundary conditions. My claim is there is no boundary conditions that you can impose. Right? Where, okay, my claim is that you take a natural choice of boundary conditions.
I mean, in this water case, you were talking about how there's this first order phase transition.
Right,
that
right.
Can get stopped, right? And
Yeah.
that you want to somehow
Correct.
say that is similar to that.
Yes, yes.
But as I cross this dotted line, I don't see anything happening, right?
You're,
I don't see gas becoming liquid or anything like
right, so it turns out that you do.
that. I do?
Yeah. So let's ask what is different between liquid, water and gas. One of the most important things about between water and gas is that water has surface tension. It has non-trivial surface behavior, which brings me to edge modes. So it turns out that no matter what you have, like this non-trivial topology is always associated with non-trivial surface behavior somewhere in the phase diagram.
So in particular, the free energy will have singularity as I cross this dotted line?
If you cross the dotted line, you'll have free energy singularities because there's a gap closure.
There's a gap closure. How can you?
So here you have one vacuum to two vacua to one vacuum. So from here to here, it's a standard first order transition. It goes like this,
Okay.
to like this.
Okay.
So yes, there is the standard kind of free energy singularity that is associated with the first order phase transition.
I see. Okay, got it. Thank you.
Right? So it turns out that if you study a natural open boundary conditions for the free theory, you end up getting a collection of edge modes. And this edge mode is a rather special variety. It
Just again, coming back to Abhishodh's question. So I'm trying to take away what I should learn about the water phase. Or whatever, these things. So your point was that these two minima just merge at the end point, right? That I suppose is some old story for water. Is that right?
yes,
And has this picture given more structure to that?
at the moment I haven't told you anything about water, but I claim that there's a version of this one can tell for water.
And version of this meaning that there is some binding in parameter space?
Yes. Correct. There's a water, let me just say a few words. The water phase diagram is naturally modeled by the Ising model in the magnetic field, and that we can track. Like we can study the theory deformations of the Ising model in the magnetic field, and the best answer that this is not published yet, but the best answer we have is that if you consider time reversal symmetry, then there's a natural two sphere that you can wrap like the critical line with. So it's a non-contractible two-sphere when you impose time reversal symmetry. That's what we believe is happening in water. Right? That's what we believe. It's not a proof, but through this mapping to Ising model in the magnetic field, we can make this argument quite solidly. So for the phase diagram has a tail where there exists a zero mode localized on the boundary. This you can see directly using microscopics. Like, you can just take the single particle Hamiltonian. It's pretty cheap. Like, it's an n by n matrix that any computer can solve, and you can find out the eigenvalues. And you can find that there's actually a locus of zero modes, which is completely supported on the edge. So this is x, right? And then just say psi 0 squared. Like if I do the calculation and then compute the zero mode eigenstate, the amplitude is localized to the edges. This we can do naturally. What do you mean?
When you talk about this wave function.
Oh, along this edge, along this line.
Along this dotted line.
Yes. Right. And field theoretically also we can find this very easily by doing a calculation a la Jacques and Rebbe, right, where one models open boundary conditions by considering domains to a fiducial vacuum. And once you do that, you can argue that no matter what your fiducial vacuum is, there's always going to be a one parameter locus where there's going to be a exact zero energy eigenstate, and there's going to be a tail that takes you there. Why SSB has edge modes? I never made such statements.
But you say that this is an SSB, right?
Yes, but this is not. Sorry, this is not the same as this. This is maybe this different symbol. So this are edge modes.
So that is not that dotted line.
This is not a dot line. Yeah.
So what is that?
So this is let's say this is the no interactions.
So u equal to 0.
Yeah.
Okay.
So it turns out that along this line, if you do a problem like Jacques and Rebbe, you will find that the exact zero energy eigenstates localized on the boundary here.
So this is some particular line in the delta J plane?
Yeah. So if it depends on how you open boundary conditions is not a monolith, right? Depends on how you terminate the boundaries. But for one choice of boundary termination, it appears here. You can make a very weird boundary termination with some potential that lives on the boundary, and this can go like.
So this is the deep in the gap phase?
Sorry.
Deep in the gap phase?
This is deep in the gap phase, but it terminates on the gapless point. It always ends up terminating, the tail terminates on the gapless theory.
So the continuum version of this is that massive fermions have a gapless mode for some phase of the mass?
Yes. So what phase depends on how you model the boundary. And
I just make my fermion, I put an interval.
correct.
Okay, I've got this two fermions, the complex fermion, and as I vary the phase of the mass, I will find a massless mode on the boundary.
Absolutely, yes. No, sorry. If you change the phase along the space.
No.
Yeah. Correct.
Changing the phase
In the bulk.
Yeah, the theory.
Yes, you do.
That should be chance related to integrating out these massive fermions to get effective chance and it only appears for certain.
Yeah. So it's related. It's not unrelated. So maybe.
This is 1 plus 1. Right?
Yeah, but there's a version of this where what you're saying is correct for higher dimensions.
And between connection with SPT or?
No, there are no SPTs. It's all extremely boring. A single trivial SPT, trivial phase. Okay.
I thought the polarization is of the inverted dimension.
Correct. So it's not an SPT.
It's not a
There's no SPT whatsoever. Whatever they are, they don't appear in this story. So it's a simple phase. The edge modes for SPTs appear in the entire phase, right? Here it appears on a tail, like this one parameter family in the phase diagram where this appears. And let me say something strange about this. Like, one could always say that, the correct criticism to make here, which one should make is that maybe I'm just parameterizing in such a way that I have just an extra fermion just lingering. So it's a 1D theory plus another fermion which has its own universe and is doing its own thing. So can I reduce this story to a one-dimensional theory plus a zero-dimensional quantum mechanical story? So it turns out it's not. So let's suppose that's true. Let's suppose that these edge modes appear because there's some level crossing happening in a quantum mechanical system that happens to sit at the end of my one-dimensional chain. Right? Let's just say that. So let's look at what happens for a what quantum mechanical system. What is the most general thing that can happen to a quantum mechanical system that is parameterized over a circle? Right? So let's say there's a quantum mechanical system that's living on the edge of a one-dimensional system. So this quantum mechanical system has its own energy levels. So I can plot energy as a function of, let me take any circle. Let me just take this circle here. Right? So theta, the gap starts off with some value, and let's say the quantum mechanical gap closes somewhere. Right? So when I go from here to here, and then the quantum mechanical gap closed. But you see, if it has to be parameters on theta, this has to come back up. It has to be a periodic function. You can only cross a gap for a quantum mechanical system for even number of points. Right? So this zero-dimensional theory that appears on the boundary, so you can actually formulate an effective theory that lives on just a point. So it is 0 plus one-dimensional theory. If you could do that, it turns out that it has a new class of anomalies. So this is the simplest version of what is called an anomaly in the space of coupling constants. So this is like Cordova, Seiberg. Unfortunately, I don't remember the other authors, but there are a bunch of them. There are more complicated versions, but this is the simplest example of what's happening over here. So the idea is that this tail of edge modes is terminating on the diabolical gapless point, and that's not a coincidence. They're intimately connected to each other in the same way that bulk boundary corresponds, in the same way as anomaly inflow does. But here it's an anomaly of a weird kind. Typically when high energy theorists think about anomalies, you have, let's say, a mixed anomaly where you have two symmetries, try to gauge one, the other one disappears. Here there was an inconsistency between the existence of symmetries and gauging. Here it's a mixed anomaly between the topology of the parameter space and the symmetries. So it's a bizarre and very interesting kind of anomaly, but they exist naturally when you have a non-trivial topology of states that appear over here. And once again, this appears through interactions also. And in fact, for what happens for this, it turns out that, let me just try this again. So there's two gapless, c equals 1/2 points, and there is a gapless line that ends over here. So this never disappears. And let me just say that in higher dimensions, this line actually becomes far more stable. It becomes a codimension 0 surface. There are dimensional reasons for why the gapless theories only appear on a line for 1D. But for any higher dimensions, the natural thing that appears is there's a shadow of gapless edge modes that appear. And this is in direct analogy with why water has surface tension. Right? So it's consistent with the whole story that I'm trying to propose, that there exists a non-contractible surface, that guarantees for you the existence of edge modes, and I believe that surface tension of water, which is a non-trivial boundary phenomenon, can be associated with precisely this in higher dimensions.
I missed this whole thing, if you don't mind.
Yeah.
One more time.
Yeah.
So let's say U is equal to 0. I understood that the claim was that at certain phases of the mass there are edge modes. Mm-hmm. And then what you said something about quantum mechanical anomalies. Could you say that again?
Yeah. So one could argue that these edge modes are completely accidental. That I just considered boundary conditions such that whenever I open it up, it pops out a fermion that's not coupled to the fermionic chain. And then what I'm looking at is this effective quantum mechanics of that decoupled fermionic mode living on the edge. The answer is no, it's not true. Because if it were true that this was a story for an isolated quantum mechanical system, and I track the energy levels of a quantum mechanical system over a circle, if there is a level crossing, it has to happen at 2 points. It always has to happen even number of points. Maybe there's no level crossing at all. That's,
You're tracking over a circle, what circle is what?
Any circle that is surrounding the origin. So here you see, this crosses the edge mode tail precisely once. In fact, I could do something like this. It will always cross an odd number of times.
Were it an autonomously defined quantum mechanical system, there would be 2.
Yes.
But because it's the boundary of a bulk, that's not.
Exactly.
Okay, but and therefore, the edge mode tells you something about the bulk, you're saying?
Yes. So the fact that this anomalous behavior is cured if you connect it to the bulk. If you look at, so okay, maybe I should have said a word importantly. This collection of states, non-trivial collection of states, actually has a name in condensed matter. It's called a Thouless charge pump. So you realize that the level that goes down disappears into the bulk. That's exactly how you cure this evenfold requirement of level crossing. What happens is this charge that sinks actually disappears into the bulk, and that's precisely this Thouless charge pump behavior.
So you need that the bulk becomes massless somewhere on your circuit.
No, the bulk is massive everywhere.
Okay, then how did this massless state disappear into?
It just the charge gets transported in this way. So it just goes into the bulk and then appears at the other end, if you would like that.
Sure. So since you also were saying that all these models, because they are philosophically like the water problem, so can I imagine a transverse field Ising model
Yes.
to 1D for this?
Yes.
So then are these the same zero energy Majorana modes that you get in the spontaneously symmetric broken phase?
No, because the whole story is in the paramagnetic phase. So it's not related to the Majorana zero modes. You see, it's not in the spontaneously symmetric broken phase. I'm focusing on the more boring paramagnetic phase in the Ising model. And these are more edge modes appear there. It's actually an edge mode there of a complex fermion, not a Majorana fermion. It's a full.
The edge modes appear in the, not in the paramagnetic, but in the spontaneously symmetric broken phase.
True. There it's a Majorana mode,
Yeah.
but this is not that.
This is in the so-called paramagnetic.
Exactly. And there the edge modes that appear are a full fermion.
But there is also a transformation you can make which maps the paramagnetic
Correct.
phase into a spontaneously symmetric broken phase.
This is Jordan Wigner.
Yeah.
Yeah, okay. Let's reserve that for the end. That's actually a very interesting question.
Sorry, just coming back.
Yeah.
You have an interval, massive fermion on an interval. Did you have this edge mode at both ends of the interval or one end?
Yes, both ends.
Both ends.
Yes.
I see. So if you look at the two ends together, that does not behave funny with quantum mechanics.
Nope.
So if you look this end and this end and treat them as the same quantum mechanics, everything is
Everything
as
is
you would
fine.
expect.
And indeed.
What is funny is that in order to behave like quantum mechanics, you need to, it's very non-local.
Yes.
That's the funny thing.
That's precisely that.
And what were you saying about something going from here and appearing there?
So if you try, so in the non-interacting model, you can track something called the 1A centers. It's a gadget that tells you where the orbitals are located, single particle orbitals are located. As you go around the circle, parametric circle, the 1A center go and then just shift and shift and then shift exactly 1 unit cell. So it's some kind of a deformation that takes you charges from one orbital and then precisely puts it on the
In
next.
the circle, where do you have these massless edge modes?
Yeah.
Wait, at what point on the circle? Only at that.
Any circle along this line. So the massless edge modes is an entire one-dimensional line.
And then you're going on a circle that cuts the line only at one
Correct.
point?
Correct.
So suddenly you see two massless edge modes and then
Correct.
they disappear.
Yes.
And what was this about charge transfer? I didn't understand it.
So let me just give a picture. It's very easily described. So let me go to the periphery of the phase diagram. So this is minus infinity, plus infinity, right? And this is plus 1 and minus 1, right? The states look very simple. The Hamiltonian becomes very, very simple. So what happens along this line is that the fermions exist only on the odd sides. 1, 2, 3, 4. As you go here, the fermion gets delocalized between 1 and 2. It's like an orbital that's delocalized between these two. So it becomes like this. So it went from 1 to somewhere between 1 and 2. If you come here, it switches occupancy. It gets localized only on the even sides. 1, 2, 3, 4. If you go up here, it's delocalized between the different bonds. Now it's between 1 and 2. Here it becomes 2 and 3. So let's track here. Started with 1, went between 1 and 2, came to 2, between 2 and 3, and then now it comes here. It goes to 3. Okay. So if you track the charge, the 1A center, if you play this as a movie, it actually shifts from 1 to 3. So it's exactly one transfer of charge from one unit cell.
And what is the connection between that and these massless modes appearing?
That and this massless modes appear. Yeah. So what happens here is that if you let's say terminate it here, this one is completely decoupled.
Okay.
Right? So you can see exactly where this charge is disappearing as you go along here. This charge is going from here, it's transported all the way around. It's not, there's place for it to go. The levels are merged into the bulk levels, energy levels.
Is it this place for it to go because at some point there were massless modes, you see? I'm trying to understand what is the connection between the existence of this transport picture you've given, which sounds clear, and the existence of these massless modes at one point on this circle.
Right. So if you look at what's happening to this zero mode here.
It's zero only at one point.
It's only on one point on the circle.
Okay, yeah.
Right? If you go to the right, it gets occupied. Right? So, so you see the first mode gets occupied here. Here it gets depleted.
You're saying this because there's a zero mode, you can have this kind of transfer without a jump in energy.
Exactly.
I see. I see.
Is your ground state degeneracy also changing?
No. Sorry, but when there's zero mode, yes, because you can put a fermion at the end, you can remove the fermion at the end. There's a ground state degeneracy.
But on closed boundary condition?
No, there isn't.
Okay, now I understood what you said for the non-interactive. For the interacting case now, what was
Sure. This is actually very cool. I mean, sorry, I've been told that saying something that I find exciting out loud to the public is not proper. But anyway, it is very cool. So you can ask, how do you model a boundary in field theory? The most natural thing to do is to consider this a fiducial vacuum. Right? So for bosonization, let me say my fiducial vacuum, this is my edge. Let's say this is my edge. This is my bulk. This entire thing is the bulk. And this is the edge. So what I do is I fix the vacuum here to be phi equal to 0. Right? So all of these things are like, I can describe this as the field just being 0 this way. Now let me say I start off anywhere. Let me start off at this point. At this point, the field expectation value is 90 degrees, pi by 2. I can ask, what is the gradient minimizing configuration that tumbles this to this configuration? Right? So in field space, in phi space, I had to go from 90 degrees to 0. The minimal gradient configuration is to smoothly connect this to this. So I can go like this, like this, like this, like this, like this, like this. There's some length scale over which the transition happens, but there's a unique path.
So these arrows mean what?
These arrows are the field configurations. So I started off with some point in the phase diagram here, where at long distances my physics is just dominated by expectation value of phi being some constant, right? So now I can just do this. You see, I can do this uniquely any point on the phase diagram, except at the antipodal point of the fiducial vacuum. Here, I can go, let's say from here, it's 180 degrees. I started off with this. I can tumble this way. Or I can do the exact opposite. I can tumble this way.
What phi was of the two boundary points were some boundary conditions?
Yeah, so the one on one side, it's just determined by where I am on the phase diagram, because RG tells me that phi is fixed to some value. I am modeling the boundary as a domain to some fiducial state, which I'm denoting here 0, but it doesn't matter what it is. The claim is whatever a fiducial vacuum is, there exists.
So you're forcing at one end of the boundary,
Yes.
phi to be something.
Exactly.
Okay. Fine.
Right? So you see that there are degeneracies exactly at phi equal to pi, which is what happens over here. In fact, you can compute the charge. There's a U1 charge you can assign, like in this bosonization framework. The U1 charge is 1 over 2 pi minus infinity to infinity dx del x phi. Okay, so you can compute the charge for this configuration and this configuration, and then take the difference between them. Right? So this is, in fact, nothing but the winding number. Right? Which is exactly equal to 1. So this tells you that the two states, the two degenerate states, first of all, A are localized only at the boundary, and B have a charge difference of 1, which is just telling you that it can be either a fermion being occupied or not occupied. So that's how it appears in the interacting theory.
You're saying this is the bosonic version of what you said in the fermionic language.
Indeed, for interactions.
Sir, why isn't it half?
What is half?
I thought that is half.
Where is half?
Because the angle difference is high.
Right. I'm looking at the difference between these two. So it's pi minus pi. So it's 2 pi divided by 2 pi.
So where in parameter space do we have these two states as?
So I'm considering any point in parameter space, and then looking at open boundary conditions, which I'm defining as like the domain to a reference vacuum.
No, but the equality is along that line, right?
Equality is along the line, yes.
When they become, when they're
Exactly,
possible.
exactly. Yeah. Okay. Okay. Finally, this whole story, like, I'm just going to stop with the physics here. I was hoping to do the same story in higher dimensions. I'll just tell, I'll just explain the mathematical framework. I should be done by 1. I'll explain the mathematical framework, which is which helps you get the answers for any dimensions, and it's a lot of fun to convert that into physics. So what is broadly, what are we doing? Let me just give things names.
So, sorry, but just to be clear, so far you solved the theory independently and then looked at
Correct.
other stuff.
Yes.
There was no prediction from
Nothing.
something for what the theory was.
Exactly.
Okay.
Yeah. No, not a theory. What I'm saying is,
What the
I'm claiming that this is going to. I can argue that this can be predicted from what we believe these things look like. So let me just say what are we looking at? Let me define I, like fancy I, to be the space ID. Let's say, to be the space of states that model the trivial phase. Okay, it's a state of boring, the space of boring states.
So are they ground states at a particular point in time?
Yes. So think about all possible Hamiltonians and that are boring, like that they are adiabatically connected to something that's a product state, and consider all possible states that could correspond to this. Like this is the space of states. I'm just giving it a name. In fact, it's more convenient to say that I'm looking at not just the trivial phase, but any phase for any periodic boundary conditions as a unique vacuum. Okay. So in fact, instead of that model, let me call this as, those things are called, for reasons, invertible states.
Is this the same as space of relevant operators modulo scale?
Modulo?
Modulo rescaling? By scale?
No.
No.
In fact, if you go to 2 dimensions, you will immediately realize it. I'll just say a few words. It turns out the answer is no. So this is the space of something called invertible states, which is not just, it's not the most boring states, but also consists of a few quite interesting states. For example, ground states of topological insulators can also belong to this. Now,
So the space I mentioned then will be larger than your space.
the space you mentioned will be larger than this.
Because certainly this space will give you some state. There will be a
Correct.
map from here to some state.
Indeed.
But there it may be many to one.
Correct.
Okay.
Right? What we want to do is study the topological properties of these states. Right? So for example, pi n of ID. For example, this is one way of studying. So let's just look at the fact that pi 0 ID are invertible phases. So if there are collection states and it's disconnected, that means that if you go from one state to another, you have to encounter something in between. You have to exit the space of these states, which is either a phase transition or an intermediate phase. So the disconnected components of this are called invertible phases in condensed matter language. And this, if you have a friend or if you or yourself have followed the excitement around topological phases in the last 20 years, is what this thing was the entire field concerned with. They were interested in disconnected components which will give distinct phases of matter. What we're interested in are more subtle properties, which are higher homotopy groups. Right? So what are homotopy groups? So these are the spaces of maps from some spheres Sn to IDs. So we're looking at the space of maps up to smooth deformations. That's exactly what homotopy theory is. So let me just give this a name. Like the standard notation is this. Okay. Now comes Kitaev's observation. And this is the part that has enormous number of evidence but no proof. The claim is that you can think of these topological spaces. This is one topological space for every non-negative integer, 0, 1, 2, 3, and so on. It's a collection of topological spaces. These topological spaces have a particular property. They form something called an omega spectrum. Sorry? Sorry, D is spatial dimensions. Sorry. In fact, to make the problem precise, we have to say, we have to fix attributes in the sense that I want to say if I'm looking at fermions or bosons, in how many spatial dimensions and what symmetries. So these are the attributes that I have to specify, nothing else. I don't have to tell you what specific kind of Hilbert space is there. Those kinds of things are irrelevant. So as long as I fix my attributes, and I only kept one of the attributes, which is the dimensionality, this space is well defined.
Characterization of this space would be just in terms of topological field, right?
No, that's a conjecture.
Topological and anti-topological or whatever. So
True. If you believe that this space is described by topological field theory, the answer is yes. But it's not clear whether that's true.
okay.
I mean, in fact, one can go very far if we consider that. There are counterexamples.
Okay. Sorry, I thought in our previous case we were looking at all states which were trivial as topological field
Yes.
theory, and yet you had some manifold.
Correct.
So it's like a bigger space than topological field theory.
Correct. That was my answer. Yeah.
Yeah.
Okay. So this forms something called an omega spectrum, which tells you the following property. So if you look at the space at d dimensions, this has the same topology, the same homotopy type as loops of d plus 1 dimensions. So the topological spaces are not independent, but if you consider the space of loops in d plus 1 dimensions, this is the same topology as the space in d dimensions.
Sorry, I didn't understand. Space. What were the two things that were the same?
So ID are the collection of topological spaces in various dimensions indexed by the dimension d.
This is the space of vacua, right?
This is the space of vacua that model ground states that are unique with periodic boundary conditions, which I am defining as invertible states, which has in its one of its components the trivial phase, where it is the most boring massive state.
But even there was some topology, right?
Even there is some topology, which is what I want to try to understand with objects like this. How do we come to the prediction part? The claim is that these.
Before you, so once this ID, I understand the space of vacua.
Yeah.
What was this omega ID plus 1? So loop, you're saying ID is the same as the topology of ID is the same as the space topology of loops
Yes. In d plus 1.
in D plus 1. What do you mean topology of loops?
Not topology, space of loops.
Space of loops.
Maps of the space of maps of a circle to the topological space.
So that's some. Sorry. So what ID is like some space.
Yes.
Some geometry.
Yes.
And the right hand side is space of maps is.
Space of maps. So you take ID plus 1 and then map S1 to this.
So that gives you some integers or something like that.
No, not integers. Why? It's just you take a loop, put it here, you take a loop, put it somewhere else. It's a space of maps.
Space of sphere.
I'm not saying homotopy class of maps. I'm not saying just space of maps.
So it's like a sigma model kind of.
Sure.
All different configurations. That looks like a much bigger space.
It is. But it's definitely a, I mean, it may be a bigger space or maybe a small space. The claim is that they have the same topology.
Loops on a sphere.
Uh-huh.
Loops on a sphere is a point.
But he's saying not up to homotopy. It's all loops.
No, up to homotopy, right? The
No, not up to homotopy. There's like, they're the same topology.
Will be characterizing topology of that.
Sure. Yeah, in that sense, it's the point.
There are two spaces which have very different dimensions, but their topology might be the same.
Yeah.
Yeah.
They're not
Will be
used.
characterizing topology.
So this is Kitaya's conjecture.
So then
Okay.
is it just pi 1 of pi d plus 1? Is it just the pi 1 of pi d plus 1?
It's not.
It's not.
Yeah. Pi 1 of ID plus 1 tells you something about this.
Yeah.
Right? So why, how does this help us? Right? It helps us enormously because, like, let's look at this. Right? It turns out that this equals Sn of ID is the same thing as this. Omega I t plus 1. There's a nice theorem in mathematics called Freudenthal suspension theorem that tells me that I can move this to here and it becomes a different mathematical operation. So sigma of a topological space is called the suspension. It's a particular thing that you can do. You can take a topological space and then you can consider a cone over it and then identify a particular spine. So you identify this line. So there's a way in which you can take a topological space and then construct a new topological space in one higher dimensions called the suspension. In particular, the suspension of an n sphere is just an n plus 1 sphere. And this is pretty cool. What I'm telling you is pi n of ID is the same as pi n plus 1 of ID plus 1. Okay? In fact, we can just go all the way. Why just say n, d and so on? What this is telling you is, if I consider n pi d, this is the same thing as S n plus d. Sorry.
You inserted pi d in the bracket.
Did I make a mistake?
SN
Sorry?
Sn
ID, sorry. Okay. So in fact, I can Sn minus d of I0 if n is greater than d. So you can go the reverse direction and then reduce the whole thing to topology of I0. I0 is nothing but the space of unique ground state of a quantum mechanical system. So the whole thing just becomes related to quantum mechanical system if n is greater than d, or this becomes S0 I d minus n if n is less than d. If you believe Kitaev, which I do, then it becomes this. So what are this? This is the topology of quantum mechanical systems. And these are distinct phases. So if you know quantum mechanics really well, and if you already classify distinct phases of matter, then you can basically figure out the topology of everything else. Now let's see what happens with this. So S1 I1 is the same as S0 I0. Right? This is what we have been working with so far. The disconnected phases of quantum mechanical systems that conserve charge is completely determined by what your ground state, the charge your ground state carries. Right? So if you have quantum mechanical systems, if you have ground state being charge 1, and then you tune parameters and you found that the ground state has charge 0, you know there's going to be a level crossing in between, which is the quantum mechanical equivalent of a phase transition. So this is clustered by charges, which is why these are called charge pumps. Right? So it turns out that this helps us enormously. There's in fact a mathematical, going from mathematics to physics, there's a recipe called, it's called the suspension construction. That tells you that if you have a Hamiltonian which has a non-trivial topological texture as we did over some kind of a sphere in d dimensions, you can use this, you can convert this into a physical picture that can help you construct a new Hamiltonian in d plus 1 dimensions. Let me call this as S1, S2. So this one is a non-trivial Hamiltonian with non-trivial winding, but not that corresponds to a 2-dimensional phase diagram, but a 3-dimensional phase diagram, and so on and so forth. So the prediction from this is that in one spatial dimension we had non-contractible loops. In 2 spatial dimensions, the most general thing I have to write down is a 3-parameter phase diagram with a non-contractible sphere, and so on and so forth and so on.
And this Kitaev conjecture, somehow I should understand it from some conceptual reduction way.
I have no idea what those words are.
And where did this loop space etc. come in?
Well, how Kitaev thinks, I don't know. Like how he came up with this conjecture is not clear.
But some rationale is offered.
So there is one can give a physical picture to this. Like one has to prove that for every loops you get a thing here, for everything here you get a loop. And there are multiple physical pictures one can assign, but none of which I would say are either intuitive or natural.
Sorry, just backing up, I haven't understood what ID is.
ID is the space of, consider all possible states that can model the ground state of a Hamiltonian, the unique ground state of a Hamiltonian. Any Hamiltonian with a unique ground state under any periodic boundary conditions.
In d dimensions.
In d dimensions.
Can I think of that as the set of low entanglement states?
It is, amongst other things, low entanglement. But low entanglement can mean many things to many people,
Right.
and
Like
that can fall.
circuit or whatever.
Yeah, things like that.
Why isn't that infinite dimensional?
It is absolutely infinite dimensional.
Okay, so it's like some very crazy space.
It's a very crazy space.
But its topology is not crazy.
Yes.
That's the point.
Yes. In fact, if you consider a general interacting system, it's a very nice space. For example, let me give you an example. The space of one-dimensional spin system is a particular thing called an Eilenberg-MacLane space, which has only one non-trivial homotopy. It has a non-trivial pi3 and nothing else. Fermions are more complex and more interesting.
The one way to see that this space is crazy, as you were saying there in the beginning, that you could just take a Hamiltonian and just assign different elements to different, just make it crazy.
Exactly, yeah. You can have a different coupling constant for
It
it.
will be the same state as the
Yeah, exactly.
as when all the couplings are equal.
Correct.
Is it about lattice systems or
Sorry?
lattice systems?
I have in my mind lattice system, but I'm sure this applies to other systems too. Okay, so this let me just say a few words which might connect to something in string theory, which supposedly is true. I don't have anything intelligent to say about it. So for free fermions, non-interacting fermions, so if you specify an omega spectrum,
Sorry, an ID, what data do you need to specify ID? Like, do you need to specify how many scalar fields you're dealing with?
No.
Or?
Like fields, it doesn't even necessarily need to be phrased in terms of fields. So the Hilbert space is not specified.
So there's something universal about all quantum field theories in d dimensions, all massive quantum field theories in d dimensions. That's what you're saying?
Trivial, not massive quantum field theories can be non-trivial. For example, Chern-Simon's theory is massive. This is not part of that.
Okay.
It's a massive field theory with a unique vacuum with periodic boundary conditions. That's a very
it doesn't matter what your fields are,
Yeah.
You can just.
Yeah.
That sounds so amazing. Where does that come from?
Kitaev's mind. I don't know. I don't know the rationale behind how this was
I
motivated.
don't mean this equality. I'm just saying that that this space is a reasonable space to consider,
Right.
and that it has some reasonable topology and so on. I mean, that sounds to me it sounds weird.
I mean, if it is a space, there is a topology that you can talk about.
But it's very simple.
But the point here is that you can characterize it. So the non-trivial part is the Kitaev.
No, but this topology is not some completely crazy.
Yeah.
Because
That's what Kitaev is saying. It's not crazy.
I suppose. Yeah. I mean, I can make more and more complicated quantum field theories.
Yes.
Will have looks like they have more and more complicated states.
Right.
I can have like some fixed point with very large central charge flows. I don't see why it all fits into one big structure.
Right.
You know.
So I mean, one
I-
kind of roughly.
Maybe one word I can say is that all these theories are local. Locality actually makes things much
You're saying
simpler.
quantum field theory. I'm
Yeah.
happy
Yeah,
with
yeah,
the
fine,
quantum
fine.
field theories, but I still don't see the space of quantum field theories is a big untamed zoo.
But this is not all quantum field theories, right? It's a quantum field theory with unique vacua.
I mean, so Shiraz,
What this is saying is that the seemingly infinite dimensional quantum field theory with unique vacua are actually not that crazy. Okay, maybe I'm just saying things in a circle. And
so if you ask even a slightly more difficult question, so where you say that let me not look at theories where you have a single ground state, right? And here he's talking about the characterization of the state space. Let me ask, how about Hamiltonians which have just gaps? Okay, and then I want to characterize them.
good, very good, yes.
Then the answer, I mean, a priori you would imagine that it's difficult, right? But the answer is
TKFT.
given by TKFT.
Yeah.
And then that there is a low energy consistency condition
Correct.
that they are classified by. Here it's kind of one refinement in the sense that you're instead of talking about theories, you're talking about states.
Correct.
Right? And then you're talking also, and there's one simplification that you're not considering the degeneracy,
Right.
but just a single ground state.
In fact, just coming to this TKFT thing, one could also ask, what happens for d-dimensional TKFTs?
Yeah.
It's actually very simple. It's not like, for given a TKFT, you can just ask what are its automorphisms, which is not very crazy, right? And then you can say there are different distinct maps from the parameter space to the automorphisms, and then you actually get a very simple topology. The only thing that's missing in for general TKFTs is this kind of a thing, that you can't tell the, given one answer, you can't tell everything else. That this is a luxury one has for very simple phases.
But what seems weird to me is that this Hilbert space can get very complicated. Let's say we just stick to this trivial TQFT. This Hilbert space can get extremely complicated. Right? It's like infinite number of fields and so on. There's no boundary. Some number of scalars, some number of fermions. Very weird things. That there is one structure for that whole thing sounds weird.
But why would you say that when characterizing TKFTs? Let's say, I mean, Lagrange could have infinity any sort of fields, and then the only thing I know is that it's close to a massive, it's a gap system, and I just want to characterize that. Even that seems a problem that is difficult to take, right? But one characterizes this in terms of number of ground states and fusion and then binding and all that.
That's true.
Yeah. But if one were very naive, one would think that all gaps, states were trivially gapped. I mean, it's a different axis, I feel. Yeah, I mean.
Because all these parameters stick around. You have to
Yeah.
all these parameters.
Yeah.
Rather than just focusing on some low energy.
Exactly. Yeah.
Okay, so just to complete the last sentence, which is, if one considers the story for just non-interacting fermions, right? It turns out that I had in my plan, but I couldn't get to the plan to do two dimensions, like use that recipe, construct a dimension model in 2 dimensions. What you end up getting is the two flavor Dirac fermions, which has 4 relevant mass parameters. There's a singlet mass, the triplet mass. But if you look at this, it's a non-trivial family over S2, which means it's a 3 parameter phase diagram that has non-trivial. Here you realize that it turns out that the triplet and the singlet masses are not independent, they commute with each other. So if you look at the actual relevant parameters for this story, the independent relevant parameters are the masses that anti-commute amongst each other along with the kinetic terms. If you look at it that way, you realize that this whole story reduces to classification of Clifford algebras. So this is where Kitaev's entry comes in. He actually points out that this was originally done, the classification of Clifford algebras related to, so this kind of a thing is, specific omega spectrum gives you something called an extraordinary cohomology theory. The relevant classification of Clifford algebras corresponds to K theory, which was apparently done in the string theory context by Hochawal. He references that in his original paper. But for this kind of a story, like classification of Clifford algebras tells you the number of independent, non-commuting, mutually anti-commuting mass terms, which actually tells the story completely. That's one thing. Second one is my concluding thoughts, which is sorry.
Parameterized just by masses somehow. This idea.
For free fermions, yes. Yes, completely. So coming to Vikram's point, we could actually take this to generate amazing examples through other procedures we know. One is given a theory with a symmetry, we can gauge it, right? By gauging, this word is used differently in different communities. By gauging, I mean like couple it to dynamical gauge fields, and you get a new theory which has all kinds of wonderful things. You end up typically with non-trivial TKFT if it's at least finite gauge fields, and then you can all of this story can be ported to that and then reinterpreted in a different theory. This dimensional interdependence is gone, but still one can construct non-trivial examples. For example, and second one is if you can do Kramers-Wanier, which is maps of paramagnitude to the ferromagnet. Their non-contractible loops have a different picture. So let me just give the final example. In spontaneously broken symmetry phases, non-trivial loops in parameter space appears through something called vacuum crossing. So let's say you have scalar field phi 4 scalar theory with spontaneously broken symmetry that looks like this. You go around the parameter space and this just deforms for the vacua to just exchange. So you start off with ground state where like for example Ising spins are all pointing up, go all along the parameter space and come back, all the Ising spins are suddenly pointing down. This is what non-contractible loops appears in like non-trivial theories that are not just completely trivial. Once again, for TKFTs there are actually more beautiful things like electromagnetic dualities and symmetry defects or things like that. But it's a story for another day. Anyway, so I'm around for the next couple of days. If you want to talk about any of this, very happy to do that.
We had quite a bit of discussion during the talk, but if there is one or two other questions.
Just wanted to understand this case ID. So let's say you have a Lagrangian. Now this ID, a point in ID correspond to some state for a specific Lagrangian. Is that?
Not any specific Lagrangian. Lagrangian with special features. It's a Lagrangian which is a massive theory with a unique vacuum under any periodic boundary conditions. So it allows for things like what I've been describing. It disallows for things like Chern-Simons theories, which has vacuum, topology dependent ground state vacuum ground degeneracy.
So let's say if you go from one point in this space ID to some other point in this space. So what is happening? What is happening to that state?
Excellent question.
Yeah.
One is if the Hilbert space does not change, your field content or whatever, then it's just changing coupling constants, bare coupling constants. If your Hilbert space is changing, it's a more interesting question, right? So this whole thing, in mathematics is related to something called stable homotopy theory, where there are two notions of equivalences. One is smooth deformations, and the other one is stacking, like you increase the Hilbert space. So from going from one to the other, you can deform either by coupling constants or coupling constant plus increasing the Hilbert space with something trivial.
Is it like going from codimension 1 to codimension 2, something like that?
No, I mean I didn't fully understand the question.
Let's say you have some weird object for ID.
Uh-huh.
Now you can go from the surface to the bulk of that object, and that's
maybe
like.
we can continue this during the lunch because it's already getting late, and I assume that you went to lunch.
Yeah. I also have another talk to give, so.
What is the other talk on?
It's a different thing. What, critical theories.
Abhishodh again.